Okay, Assalamualaikum. Good afternoon. Can you hear me? All right. Okay, that's good. Apa khabar semua? Sihat? Loud and clear. Good. Okay, Alhamdulillah. Sekejap eh. Yang ada dalam USM still dalam USM kan? USM tak bagi balik lagi kan? Okay, okay, alright. Okay, hold on. Anak saya pun ada Google Classroom. Ketiga juga, so hmm, semua online learning sekarang. Okay, so let us continue with our lecture. So today we're gonna continue on PN junction under equilibrium still. So this Wednesday, I'm gonna give you some information after the class in the group. So about the open book test, right? Test one. So I told you last time it's gonna take 24 hours open book, and you're gonna need to answer and later upload on eLearn platform, just like the way you did for your assignment one, right? All right. Some other details I'll give you after the class in our WhatsApp group. So there is no class Wednesday morning, so you can start answering your. I will upload your test one questions right before the class, so you can start work out your test one during the class, and yeah, whatever you don't have other classes as well. So altogether there'll be 4 questions, open book question that you can search on internet or cross check with your lecture notes and stuff. Okay, I'm going to give you the instructions later on after the class. One more thing, the test one is essay based, right? It's based on essays. It's based on explanation, right? So just take note on that. Okay, so let me now share the page. Hold on. Okay, all right. Let me share the lecture page. All right. All right. So you can now see the page, right? Please reply. Okay, that's good. All right. So last time we stopped somewhere here. So we've discussed that the moment you have PN junction, the moment you have got your P and N semiconductor materials in contact with each other, so we're gonna have alignment of Fermi level to only one Fermi level, right? So before you join, you have Fermi level of P-type on the left-hand side. The Fermi level of P-type closer to the valence band, and then you're going to have your Fermi level of your N-type closer to the conduction band. So they are pretty much like this. If you want to plot in energy and distance diagram, right? So the moment you join them together, so the moment you're going to have a metallurgical contact in the center, so you're going to end up with diffusion of both carrier types into both directions. So the holes in p-type the holes in p-type are going to diffuse into n-type, and the electrons in the n-type are going to diffuse into p-type, right? So until some point where they no longer diffuse, and at that point you have your built-in electric field, right? So in that condition, we call it as thermal equilibrium, the new thermal equilibrium. So at that particular point, you're going to have your Fermi level for your PN junction as a new one, only one, right? Only new one. So we have also learned last time that before you join, the majority carrier in the n-type is given by Na, or also equal to pp naught. So we're going to mention pp naught, pn naught a lot right after this, because you're going to do a lot of calculations based on the related equations. So Na is equal to pp naught, and therefore the minority carrier in p-type is electron. So therefore we call it np naught, which is density of electrons in p-type material at thermal equilibrium, right? And that's given by Ni squared over Na. So if you look at n-type, so let's recap. So the dopant is Nd because it's n-type, so donor concentration, which is also equal to Nn naught, density of electrons in n-type material at thermal equilibrium. Therefore, the minority carrier is whole. So, and that's given by Pn naught, right? A density of holes in n-type material at thermal equilibrium, and that is given by Ni squared over Nd, right? So you need to be able to plot, not plot, you need to be able to draw this, the bottom diagram here. You need to be able to draw this. You should be able to. Why is it not coming? Yeah, it's a bit late. Wait, hold on. Okay, you should be able to draw this, okay, the whole thing. So make sure you are able to draw this energy and distance for both materials before they join and after they join, right? So make sure you are able to draw that. Okay, so let's move on to the next page. So after they are already a PN junction, so you can see how the diagram changes from the previous page into the current page. So uh, the the concentrations of both carriers are still the same, just like the original one, right? Left and right. So look at now the EF, the new Fermi level is only one. New Fermi level is only one for the PN junction system, if you like, PN junction system. It's only one. So um, it's only one EF, and then you're gonna have a banding here in the center, in the central region where we have the space charge, right? So the depletion region, the space charge regions are all in between, right? In between. So the moment you have a diffusion of carriers into both sides, and then we're gonna slowly end up with space charge region, which is made of the ionized atoms due to the losing of holes and electrons in the depletion region. Hold on, kejap eh, kejap eh. Kejap lagi, kejap lagi. Sorry ya, nak saya pun tunggu tengah tunggu Google Classroom punya setting. Okay, all right. Where was I? Yeah, depletion region, which is made of ionized atoms due to losing electrons or holes, right? Due to losing electrons or hole into the other type of the p-n junction. So you're going to end up with a barrier height here. Barrier height is given by q psi naught, or also called qvbi, right? So you can replace this with vbi, qvbi. Okay. So we're going to have in total 4 currents due to diffusion of electrons and holes, and then drift of electron and holes. So make sure you know how to draw the flow of the currents, right? Both electrons up here for the red one, drift and diffusion, and then for holes down here, drift and diffusion as well. Okay, so new page. So at the interface, we already have a potential barrier. We call it potential barrier or energy barrier. So it's given by Q psi naught, or you can also say QVBI. QVBI dengan ni sama. So that is the barrier at the middle of the junction. So in order for us to calculate how much is the potential barrier, so we'll use this equation. So VBI, so this one is actually VBI. So it's equal to thermal voltage VT ln NA times ND over NI squared. So NA is your acceptor concentration, which is also equal to NA is what, P type, right? So it's PP naught, so also equal to PP naught. So ND, is what? What is ND then? If you want to replace NN naught, right? So ND is NN naught. Okay. Density of electrons in N type at thermal equilibrium divided by Ni squared. Then you're going to have your VBI. Okay, you're going to have your VBI. So kalau you nak tahu macam mana dapat the derivation, you can look at this portion, the upper portion, right? So this upper portion is actually derived from the, if you go to the previous page, another page, all right, if you derive this, if you want to derive this, you can have a look at this drawing. You have E1 here, the distance between your EF and EV, and this one is the distance between EF and CB, and then you minus with the band gap EG, then you're gonna end up with this, right? EG minus E1 minus E2, and then you replace, but you don't have you can work out yourself, but most importantly you have to know that this is the final equation that you have to use for VBI. Okay, so if you look at this equation, it can also be rewritten as the below one, right? So because we know that NA is equal to PP naught and ND is equal to NN naught, and N, you can take this NA over NI squared, and then you can replace, or you can also replace, you can either do, replace PP naught or NN naught over NI squared to be able to calculate NA or ND, and then you're going to end up with this. So they are same thing here. They are same thing. So therefore VBI is also equal to VT ln PP naught over PN naught, and also equal to VT ln NN naught over NP naught, right? So if you look at this equation, they are actually holes. So both are holes. The top one is in the majority carrier concentration region, and this one is the minority carrier region, right? So majority for N, and minority in P. Majority in N, minority in P, majority in P, minority in N, right? Okay, so you can just replace the the Ni squared over whatever that we have learned from the law of mass action into the top equation, and then you can rearrange the equation to get the below one. Right. After rearrangement, you also can write the equation as this. Okay. Sama macam last page. So VBI, this one is equal to VBI also equal to a psi, also equal to thermal voltage ln PP naught over PN naught, also equal to VT ln NN naught over NP naught. And if you rearrange this part, the first part of the equation, to be able to calculate minority carrier concentration, this one is minority. Okay. So kita sekarang ni daripada top equation ni kita nak kena kira PN naught and NP naught, right? This one, if you look at this, the first line is PN naught, or you can also define that as density of hole in N-type at thermal equilibrium, which depends on PP naught or NA times exponential negative Q VBI over KT. And if you want to calculate minority carrier electron in P-type or NP naught, and that's given by NN naught, which is ND, times exponential of negative Q VBI over KT. So kenapa kita nak kena calculate ni? Because if you look at this diagram, the below diagram, okay, sekarang you tengok dekat diagram ni, you tell me which side is P-type, which side is N-type. You tengok diagram tu, you tengok which side is P-type, which side is N-type. Sementara saya nak tengok telegramnya. You write down first, okay, I'll have a look in a few seconds. Hold on, yeah, I need to get the telegram. Okay, so what is it? Okay, let me check. P-type left and type right. Okay, P-type left and type right. Okay, all correct, good. So kiri P-type, kanan N-type, right? It's quite simple, right? Because you boleh compare majority carrier concentration and minority carrier concentration yang mana lagi tinggi kan. So since on the left hand side, the highest one is PP naught or NA, so therefore it's P-type. So bila you tengok the profile of the carrier from left to right, from P to N, so you can see that the concentration of carrier changes like this, right? It goes down through the depletion region. This one, the center one is the depletion region. So and it goes down into this sort of profile in N-type. So let's recap. On the left hand side, P-type is the hole is the majority carrier, electron is the minority carrier. Okay, so on the right hand side, dalam N-type, electron is the majority carrier, hole is the minority carrier. Okay, so minority carrier is always given by Ni squared over Na, and majority carrier is always given by the approximation of Na or Nd. Yeah? So approximately Na or Nd, assuming 100% ionization. Okay, so now the moment we know that PP naught is approximately equal to Na, we want to know how much is the minority carrier concentration hole on the right hand side. So if you look at this, yeah, hold on. Hold on. Okay, So we want to know how much is the carrier concentration of hole on the right hand side. Okay, kita dah tahu hole banyak mana dekat dalam p-type sebab dia majority carrier. But we want to know how much is hole on the right hand side. So notice that hole is the majority in p-type, and when you go to the right, hole is now the minority carrier. So bila you have diffusion, bila you join p and n together, so hole yang cross into the n type will be minority carrier. So we want to know how much exactly is the hole. So to be able to calculate, we have to use this equation, the top one, go to here, P N naught, you have to use this equation, right? You have to use this equation. P N naught is equal to PP naught, which is equal to majority carrier concentration times exponential Q VBI. So therefore, you have to calculate the VBI first, right? Calculate the VBI first from the previous page punya equation, and then over the thermal voltage, KT. Then you know how much is your hole concentration in N-type material. So therefore, you can also calculate electrons on the left hand side as well, because electron is the majority on the right hand side, and then it goes off like this, and then electron becomes minority on the left hand side. So you want to also know how much is the exact concentration of electrons in p-type material after they are diffused, right? And that will be given by np naught. That will be given by np naught equal to nn naught exponential q sine or vbi over kt. Okay. Is it okay? Faham tak? Sekejap saya nak check Google Classroom saya punya anak. Is it okay so far? Sorry for the delay. Okay, hold on. Kelas sekolah rendah pun clash juga sekarang through Google Classroom. So using the same phone, same line. Cuma ada extra laptop je. Sekejap, let me get some details for my son. 1 minute ya. No link. Okay, right. So is it okay? Oh, tak faham ke Syah? Okay, which part did you miss? Syaira, which part did you miss? You can type here, then I'll go through once again. Diagram, right? Diagram. Okay, hold on. Yang lain okay ke diagram? Are you clear? Let me. Kecil pula dia ni. So small. Lain okay. Senang pun tak faham Okay, right. Kurang faham sikit, okay. Alah, kecilnya dia punya eraser ni. Okay, let me explain again about the diagram. Equation tu relate dengan diagram ke? Yes, of course. Let me explain again the diagram. Eraser dia too small How do I get? Too slow. Okay, anyway, I'll just go through. Okay, so diagram ni, okay, diagram ni related to the equation above it. So if you look at the equation of Pn naught equal to Pp naught exponential negative Q psi to VBI, sama, potential built-in potential, right? So that's equal to built-in potential over KT. That's equation in the first row. So equation in the second row says NP naught equal to NN naught times exponential negative QVBI or psi naught over KT, right? So how is it related? How is it related? So kita tengok dekat hole dulu, kita tengok dekat yang atas dulu. Okay, let's look at this, okay? P and naught, kita tengok yang first. Sekarang, okay. To be able to, okay, bila kita join P and N material together to form a PN junction, the moment you join, hole is the majority carrier on the left hand side, right? And electron is the majority carrier on the right hand side, right? So the moment you join them together, holes on the left akan diffuse ke kanan, masuk ke N-type. Hole asal daripada P-type, majority carrier, akan diffuse into N-type material. So hole will diffuse from left to right. Okay, left to right. Dah banyak buat diagram ni, jap. Try padam tapi dia punya too small. Sekejap, bagi saya padam ya, so that I can kecil sangat pula dia punya eraser ni. P and naught P and naught equal P and naught equation yang ada QVBI P and naught equation. Yang mana ni Jasmine? Page ni ke? Okay, hold on. Okay, yang equation yang paling atas tu you just KIV je sebab itu memang asal equation, but then if you want to calculate the concentration based on this diagram, kita kena rearrange the equation into the center middle punya equation. Right? Sekejap saya tunjuk saya padam ni, kalau tidak nanti tak nampak. Okay lah, boleh lah ni Okay, let me draw again. Okay, so equation yang atas ni that's what you get after you rearrange the previous page punya equation. But just KIV the thing first. Tapi sebenarnya equation yang you dapat bawah ni is actually the equation yang you derive from the top equation anyway. You just tukar dia punya perkara aja, dia punya headline, right? Dia tukar punya headline to be able to get this. Okay? To be able to get this middle equation. So I want you to focus on the middle equation now. The P and naught here and NP naught, okay? Yang atas tu before kita rearrange. Yang middle here is after we rearrange. So in order to explain the figure below, we want to use the middle equations. Supaya you tak confused lah. It's actually from the same origin, tapi yang ni dah dipermudahkan supaya it can reflect the content of the equation of the diagram at the bottom of the page. Okay, so now after you join P-type and N-type, hole is the majority carrier on the left hand side in the P-type. So apa akan jadi? Hole akan diffuse from left to right, right? Betul? Itu okay kan? Clear? Let's talk about hole first. Is it okay? Alright. So hole is going to diffuse from left to right. So pada masa sama kita tahu lah electron akan diffuse from right to left, tapi I don't want to touch that just yet. So hole is going to diffuse from left to right. So we already know the PP naught. We already know the value of PP naught sebab that's given by Na, kan? Kita dah tahu the doping level. If Na is given, then you know your PP naught already because they are equal. Okay? However, you don't know your Pn naught yet. This Pn naught on the right hand side for hole, you don't know yet. Sebab the moment it diffuses into N-type. Sekarang ni kita tahu value kat sini, but then the moment it diffuses into N-type, we don't know the value here. At this point, we don't know yet. Right? So, if you don't know yet, you have to calculate. So, how to calculate? that will be given by this equation. The first row ni, yang equation 1 tadi tu, yang sebulat. P and naught will be given by PP naught times exponential negative QVBI over KT. Then you will know your P and naught. Okay? So one more thing, remember, after your hole diffuse from left to right, dekat kiri tadi hole jadi majority kan? Dekat kiri hole is the majority. The moment it diffuses into the n-type material, hole akan jadi minority. Yang asal pun memang dia dah minority dah kan? Dia dah majority, n-type, hole is minority. So bila dia masuk kat sini, yes, it confirms the concept lah. So dia akan jadi minority carrier concentration. Okay? Okay, so I rasa you confuse antara dua benda sekarang. Satu, there are two things that we want to consider before we move on. First, okay, if you look at only one side, right, left hand side, okay, sebelum kita proceed, saya rasa you confuse kat sini kot. Sebelum kita proceed, okay, if you look at only in the p-type material, jangan tengok diffusion lagi. Saya kita continue. Hole is the majority in p-type, right? Okay, and hole concentration is given by Na, right? So, and also equal to PP naught. Okay, so that's very clear. So, at the same time, in the p-type material, electron is the minority carrier concentration. Okay, electron is the minority carrier concentration. So, dalam p-type material ni, electron punya concentration is given by Ni squared over Na. Okay, Ni squared over Na. So that's one thing. Tu cerita sebelum dia diffuse. Tu cerita dalam p-type material saja. Okay? Is it okay so far? Dalam p-type material saja. Okay, good. So the moment hole dah P and N junction, P and N material join, you akan dapat P N junction. Sekarang ni bila hole yang majority tadi diffuse into n-type, hole ni dia akan jadi minority in n-type juga. So dia akan jadi minority in n-type. But you don't know how much holes have diffused into this n-type material. So in this condition, you have to use Pn naught, Pp naught times EQ negative QVBI over KT in order to determine the value of Pn naught. Okay? So maksudnya ada dua benda lah. Satu benda ialah majority and minority sebelum dia diffuse dalam material tu, either P-type or N-type. Second thing, the equation yang kat middle tadi tu, yang time exponential tu will be the diffusion punya proses. So majority kat sini, the moment it diffuses, it will form minority carrier on the other side as well. So equation yang you perlu guna untuk determine that concentration of hole tadi tu, yang diffuse, is exponential punya equation tu. So two different things, okay? So the same goes to n-type. So if you look at n-type, before diffuse, this is the majority and minority. So majority is given by Nd or Nn naught. Minority is given by Pn naught equal to Ni squared over Nd. But the moment electrons diffuse from right to left, bila diturun ke sini, kalau you nak tahu dia punya value kat sini, you kena guna equation ada exponential punya component. Okay? So is it okay? So two things, okay? Two things. Okay, So law of KLIA, bukan international airport, right? What is it? Alright. So before it diffuses, you have to use law of mass action untuk minority. Tu tip dia. So after it diffuses, you have to use the exponential component to calculate the minority. So it makes sense, right? The moment it goes down, it will become exponential component lah. So therefore you have to use exponential component. Kalau yang tadi tu is just within the same material itself. So therefore you have to use a law of mass action. Okay? So, all right. So that diagram. So let's move on to the next page. this is also the PN junction as well. So if you look at this is a plot of space charge density. Space charge density is given by this equation. Then you can notice that you have the charge neutrality component in the equation. So at room temperature, the space charge plot looks like this. So the y-axis is the charge, the x-axis is the distance across the PN junction, right? So if you want to put the whole block of PN junction, it will look something like this. If you draw, it's going to be something like this. Okay, if you can do a border here, you can draw a border here. Okay, this region and this region is the quasi-neutral region, bukan depletion region. There's not space charge region. Ni Q&R, quasi-neutral region. So in this middle region, it's called depletion region or space charge region. Okay, space charge region or depletion region. Konsep sama je, P-type or N-type, cuma kiri, kanan, kanan, kiri. Yes, sama je. Yes, sama je, kiri, kanan, kanan, kiri. So if you look at this diagram now, you tell me which one is P-type, which one is N-type. You tengok block diagram yang saya draw tadi on top of the charge punya diagram. Which side is the P-type, which side is the N-type? Anyone? Sama je kan? Kiri P, yes, Azrizal. Good. Kiri P, kanan N, sama je. Right? Kiri is P-type. So the whole thing here is actually P-type. So the whole thing on the right is N-type. Okay, sebab apa you kata P-type? Sebab dia punya charge negatif kan? Sebab charge dia negatif. So why is it negative? Sebab kita dah tengok tadi dia punya P-type holes akan meninggalkan P-type punya region, akan menyebabkan region tu jadi negatif. So on the other hand, if you look at right hand side, you akan dapat charge yang positif. Macam mula-mula kita tengok PN junction dulu. Because electrons leaving the region menyebabkan dia depleted of electrons, therefore it becomes positive region. Okay, so left hand side is P-type, right hand side is N-type. So if you talk about charge, then only depletion region yang ada charge. So depletion region sahaja yang ada charge. So you can see here, that's why in this plot you don't have any magnitude of the charges in the quasi-neutral region. So dekat sini kosong, nothing. Dekat sini nothing. But you have the charges here in depletion region and also here in depletion region. And they are of equal areas. Okay, they are of equal areas, right? So the two harms are due to the immobilized ionized dopant atom due to them losing either holes on the P-type or electrons on N-type. A large electric field is associated with these two harms. So the moment you have this space charge region, so it's going to develop electric field across this depletion region. Do we have electric field in quasi-neutral region? What do you think? Do you have an electric field across quasi-neutral region? Ada tak? Yes. Why yes? Jasmine, what do you think yes? Okay, how do you get electric field? Zero electric field, right? Kenapa zero electric field? Kenapa kita ada yes? It's actually zero. So that electric force. Okay, there's no charge. If you look at quasi-neutral region, you tengok dia punya charge punya plot ni. On the y-axis, there is no charge in the quasi-neutral region, either P-type or N-type. So the moment dia tak ada polarity, dia tak ada charge, there will not be any electric field. Sebab electric field dia kena ada positive and negative punya charges, then only it will develop, right? From one direction to the other direction. Kalau you letak neutral region punya region, then there's no electric field. So that means, in this case, we only have electric field at the junction. Electric field only in the junction. Okay. So if you can recall last time, kita ada discuss tentang carrier drift, right? Carrier drift due to drift of electrons and drift of holes near the junction, right? And if you go back and watch again the animation on PVCD-ROM, you can see that positive charge in the n-type akan tarik elektron, right? Positive charge dalam n-type akan tarik elektron dan dia akan tarik elektron masuk ke n-type. So therefore you can attract electrons into n-type, and therefore you can also attract holes into p-type. And these two mechanisms will lead to drift current due to electrons and due to holes. So if you notice, the moment you do that, you do drift of electron to one side and drift of holes to another side, we are actually separating electrons and holes, right? We are actually separating electrons and holes. Kenapa kita nak separatekan electron and holes? Anyone? Kenapa kita nak separatekan electron and hole in this case? Kita nak tarik electron to one side, and then kita nak tarik hole into the other side. Why do you think we want to do that? Mobile carrier tu boleh pergi mana-mana, dan sebab tu dia kosong at certain place and not electric field. Right, you want to, nanti kita akan discuss about semiconductor device. Okay, at PN junction, we want the PN junction to help separate electron hole pairs. Remember last time kita ada bincang tentang generation kan? So for example, if you want to do illumination on your silicon, for example, bila you illuminate using photon energy more than your band gap or equal to your band gap, you generate electron hole pairs kan? So the moment you have electron hole pairs generated in your semiconductor material, you don't want them to, you dah generate electron hole pair, they are broken free from each other. You don't want them to what? You don't want them to recombine. Great. Yes, exactly. So kita dah generate electron hole pair, kita dah pecahkan electron hole pair so that they move to the other direction. So bila kita dah generate electron hole pair, we don't want them to meet again in the device. Anywhere in the device, we don't want them to meet. Unless if you want to fabricate LED. Right? So if you want to fabricate LED, you want them to meet. So that's a little bit different because you want them to meet and recombine radiatively only so that they emit light. Right? They emit light, then you get your light, then you get your LED. In other devices like transistors, detectors, solar cells, you don't want the carriers that you have generated, electron and hole, to meet again anywhere in the device. So kita tak nak depa recombine, right? Kita tak nak dia recombine. So what do we do then in order for us to avoid them to recombine? We use electric field at the junction to attract electron into one direction and attract hole into another direction. So bila you tarik electron into one direction, hole into the other direction, you are actually separating electron hole pairs from recombining. So barulah carrier ni tak akan recombine dalam device sebab dia dah ada direction nak pergi. Due to the electric field tadi. Sebab kita dah ada drift component. So bila electron dah pergi into one direction, hole dah pergi into another direction. If you remember last time I draw ada metal contact dekat atas, metal contact kat bawah kan. So electron akan masuk ke n-type. So hole akan pergi ke p-type. So dekat hujung silicon tu ada metal contact and another end we have a metal contact as well. So then they are collected at the metal contact, then you can see your IV curve. Then only it is successful. Kalau kita ada PN junction, there will not be any effective carrier separation. because there is no electric field to help separate electron hole pairs. Therefore, if there is no electric field, last time you remember, kalau tak ada electric field, macam mana carrier to move? Still remember? Can recall? Kalau tak ada electric field, macam mana carrier to move? Anyone? Kalau tak ada electric field, how does it move? Kalau ada diffusion, there'll be diffusion, right? Kalau you letak semua particle tu dalam satu box, for example, there's no electric field in the box. So how do they move? They will move randomly. Yes, Ain, exactly, good. They'll move freely, randomly. They'll just move. Dia akan langgar dinding, scatter into each other. They'll have collision, all those stuff, mean free path. They'll move perfectly randomly. Sebab dia tak ada direction yang dia nak follow. So the moment kita ada electric field at the junction, we will direct the carriers to move into specific direction. Then electrons will move into N-type, holes will move into P-type, and at the same time, we are actually separating the carriers from recombination process. Barulah kita akan dapat output at our metal contact. Bila you measure, you buat project, you buat device, PN junction or whatever, you measure you punya satu electrode negative on one metal contact, satu electrode positive on one metal contact, another metal contact, sorry. Then you measure, you dapat curve. That means you are successful in separating your carriers at the junction already. Kalau you tak nampak any result, that means the carriers are just generated inside but they don't survive. They recombine somewhere inside your silicon or inside germanium, inside your whatever material. They recombine, tak sempat sampai metal contact pun. They recombine already based on their diffusion length, L equals square root d tau. Then you don't manage to extract them outside to the outer circuit, then you see nothing, right? So that's why we have PN junction. Is it okay? Is it clear? Okay, faham? Right. So sekarang ni kita ada PN junction to help separate the carriers into their own specific direction. Okay, good. So now, we are now at the next page. So let's go for another 5 minutes maybe. Okay, this is called depletion approximation. So we're talking about depletion region approximation. So we're talking about depletion region only. So we're not talking about quasi-neutral region at all. Just the central region, right? The area where you have the positive charges and negative charges only, right? So the first curve here, the top one is the charge curve against the distance through the material, through the PN junction. So kita boleh nampak the right hand side is the positive charges. That's why it's positive on the y-axis. The left hand side is negative charges. That's why it goes to the negative direction on the y-axis. And then if you calculate the electric field, that will be given by this equation and this curve, right? So you can see from here the electric field is only within this area, within this depletion region, okay? So the second one is the electric field, Poisson equation, and the third one is your bad number. Number 3 ni VBI, VBI. So yeah, wrong chat, sorry. Saya pakai cursor je. If I have stylus, then it would be better. Okay, so yes, so that will be your potential, built-in potential across the junction. Okay, so in the space charge region, the carrier densities N and P are assumed to be negligible compared to NA and ND. So kenapa negligible? Because this is depletion region. So depletion region, that means the regions are depleted of carrier. Dia tak ada carrier sangat. Dia tak ada carrier sangat berbanding dengan NA or ND outside the region. So NA and ND here is referring to the quasi-neutral region outside depletion on this side and outside depletion on the other side as well, right? So outside the depletion region, the charge is equal to 0. So that's why you have this step change in the curve, okay? Step change in the curve, square shape, right? So this one is correct if you assume uniform doping across. Kalau you punya P-type and N-type material tak ada uniform doping, then this one is not accurate. Maksudnya dia ada changes lah. Tapi for simplicity, we only talk about uniform doping. Right, let's do another 1 or 2 pages. How many pages do we have? Yes, Poisson is for the closed form solution. Yes, right. Okay, let's look at this. Okay, this example. Kita go through this example, then we stop. Okay. Kita try buat this calculation. Consider a silicon PN junction at 300 Kelvin with doping concentration of Na 2 times 1017, and then Nd is 1015. So that means you have P-type 10 times 17. Then you're going to join with N-type 1015, right? 2 times 17 and 2 times 15. Sorry, 10 times 15. So calculate the built-in potential barrier at the junction. Assume Ni is equal to 1.5. Well, you can also use 1.0 for this. So we go back to this equation tadi tu. Wait, back page is it? Yep, right. So this one, the built-in voltage equation. So VBI is equal to thermal voltage time ln NA squared. NA squared. Okay. So VBI is equal to thermal voltage times ln NA squared over NS squared. So thermal voltage is known, ln Na is known, Nd is known, NS squared is known. You can also replace this with 1.0 times 1 to the 10, and then you're going to have 0.7 volts, 0.713 volts. So this is the built-in potential at the junction. So maksudnya, bila you ada thermal equilibrium, you akan ada, due to the presence of depletion region in the middle, you're going to develop potential voltage of 0.713 volt at the junction. So if you want to know the barrier height at the junction, QVBI, so you just times this value with Q. You kali dengan electron charge, then you're going to get your barrier height at the junction, right? Remember the PN junction punya Venn diagram drawing? So at the bottom there, you can label your QVBI barrier height, and that barrier height will be given by Q times this voltage. So that will be the barrier height that is stopping your electrons and holes from further diffusion. Okay, so this is the barrier height that stops your electrons and holes from further diffusion. The moment, if you want them to diffuse again, sekarang bila you dah ada barrier height tu, you are actually at a new thermal equilibrium. So, and the carriers cannot move already. Carriers cannot diffuse already. Holes cannot diffuse into N-type already, and electrons in N-type cannot diffuse into P-type already because dah ada barrier height dekat tengah, dah ada tembok. To be able to move again, right? What do you think we have to do? Kalau kita nak removekan, kalau kita nak make sure the carriers move again after equilibrium, what do you think we have to do? Any ideas? No idea? Okay, sekarang you ada barrier height dekat tengah, then you tak boleh move sebab ada tembok kat depan. So, kalau you nak cross juga, what do? You pecahkan tembok tu lah, pecahkan tembok tu. So, in this case, in the future, in the next lecture, we're going to learn on how do we do that. So, it's called reducing barrier height by applying bias. So, maksudnya you kena apply voltage, some voltage to the P side and to the N side in order to reduce barrier height, to be able to remove it ataupun rendahkan barrier height so that your carriers can diffuse again. Hole can diffuse again from P-type into N-type, electrons can start diffusing again from N-type into P-type and re-establish the new equilibrium. Okay? Macam mana nak dapatkan value VT? Oh, VT is the thermal voltage. KT over Q. Right? VT is given by KT over Q. VT KT over Q. Izian tanya what is 1, 2, 3? What is 1, 2, 3? Izian, which one? Which page? Page. Sorry, I lost track already. Which page? Depletion approximation. Oh, okay, hold on. Oh yeah, you know this number? 1, 2, 3 ni curve punya number je, curve number. Page 22, right? Nah, this one. So this 1, 2, 3, right? On the left, right? Ni curve punya number je, curve number 1, curve number 2, curve number 3. Tadi saya explain curve number 1 is for the charge and curve number 2 is for electric field, curve number 3 is for built-in voltage. Okay, so any other question? Alright, okay. Ada soalan lagi ke? Kalau tak ada, Rabu ni there is no class, right? You gotta do your test 1. Lagi saya akan bagi some detail on test 1. And then I'm gonna upload the questions right before the session. Right before the session so that you can start work on test 1 from 9 a.m. Okay? Alright, so far so good. Then on Thursday, we're going to continue with this. Space, charge, width, and then we're going to move on to PN junction under applied bias. Sampai topik mana? Okay, the test 1 is from day 1 of our lecture until PN junction under equilibrium. Tapi depletion width pun ni tak masuk Depletion width pun tak masuk. Sampai konsep of PN junction only. But it's open book anyway, so you can always check your lecture notes. You can go online. You can search for papers if you want to, or some other references. Okay. So from day 1 of our lecture until PN junction under equilibrium. Tapi yang space charge semua ni tak masuk lah. The few front pages of your PN junction punya slide je. On what is PN junction, how does it work, what is it actually doing. Okay, Syah? Ada siapa-siapa lagi ada soalan? Ada? Okay, hold on, I'll stop sharing this. Okay, so okay, don't kena tengok balik je. Yes, you tengok balik je nota ni. And previous note as well. Okay, so what else? Okay, for today, tadi saya dah beritahu dalam group, saya dah set multiple session punya attendance. So that means one post for Monday, one post for Wednesday, one for Thursday, one for Friday. But for Monday, it will cover every Monday onwards. Today and onwards, okay? So you kena tick dekat same post every time lah. So you just tick for your attendance and I'll see if you have any problem or not. If you have any problem ticking the attendance or it doesn't activate or whatever, just let me know, okay? Sebab sebelum ni saya buat one by one, day by day. So I'll try to do multiple sessions one shot so that I don't have to waste my time doing every single time. So you try to do it and I'll see how does it work, okay? If you have any problem, just let me know. Okay, kalau tak ada apa-apa, I think that's all for today and prepare for your test 1 open book. I'll give further instructions later on. Right then, thank you very much. Assalamualaikum, bye-bye.